So, the first lecture is going to be a bit of a long one because I'm making up for the fact that on Monday we really didn't do any math at all. So we're going to start with a bit of a review of integrals and specifically what they mean. So some days are going to be sort of theory heavy and then other days are going to be just example heavy. Since this lecture is a bit of a longer one, it's going to be a bit of both. So first off, I want to sort of motivate calculus a little bit from the position of physics. So suppose a particle is moving in a straight line along the y-axis. Doesn't need to be moving in one direction. It can move up, stop, move down, and move up again. So it's moving in an arbitrary fashion, but it's constrained to a straight line. We click a stopwatch and observe the position of the particle on the y-axis. So for example, let's say that we observe the following data. So t is the reading on the stopwatch, and y is the corresponding position on the y-axis that we observe the particle at. These could be seconds, minutes, it doesn't really matter. These are units of second, or units of time, these are units of length. Doesn't matter what they are. So, in this case, we can conclude that the particle is obeying a pretty simple relation, namely, y appears to always be the square of the corresponding reading on the stopwatch. So y is equal to t squared. Now in general, let's say that the particle obeys the relation y is equal to f of t, right? So the position on the y-axis is some function of the corresponding time on the stopwatch. Doesn't have to be as simple as t squared, but it's something. So f is some arbitrary function. A natural question arises. When the reading on the stopwatch is t, what is the instantaneous velocity of the particle? So in Calculus 1, this was one of the motivating questions, and we determined that the instantaneous velocity is given by the derivative of the function. So just recall, we have a number of notations for derivative. We could say d by dt, where this down here is whatever variable is inside the function. I prefer just using a prime, or even if you want to be really, or just like y prime, if you want to be really, really space conscious. I'm probably going to try using this notation for the most part, just this f prime. So most of Calculus 1 is devoted to the study of rules for determining the derivative of a given function. That's called differentiation, right? So, product rule, chain rule, quotient rule. There's a whole bunch of rules that you spent a whole lot of time in homeworks, just sort of drilling into your head. Incidentally, now is a good time to review those rules if you've forgotten any of them. So in our example, the function f of t equals t squared has a derivative 2t, and that's just a consequence of the power rule, right? If you have a power function and you want to differentiate it, just take the exponent, move it down front, and then subtract 1 from the exponent. So the point I'm trying to make here is that if this function, this arbitrary function, denotes the position of the particle on a straight line, then the derivative gives the velocity of that particle. That's Calculus 1 in a nutshell. I mean, there's some other stuff you do, but that's the motivator. Now, let's look at the same situation in reverse. Let's suppose now that the function f denotes the velocity of the particle, okay? So now whenever you see the function f, think of that as being velocity. How do we determine the total distance the particle travels over a given period of time, say from t equals a to t equals b, where b is larger than a? Well, if the velocity is constant, then this is easy. Then this is a high school physics problem. Velocity is measured in units of length divided by units of time, so like meters per second or miles per hour. So if the particle is moving at a constant, emphasis on constant here, say 5 miles per hour, then the distance traveled by the particle in 2 hours is just, well, multiply the velocity by the time. These hours cancel out, so we just get 5 times 2, which is 10 miles. Right, that's just ordinary dimensional analysis. Just dealing with the units of things to get them to, to get the correct units out of it. So more generally, constant velocity times length of time equals the distance traveled during that time. Okay? So if the velocity satisfies f of t equals c over the time interval from t equals a to t equals b, then we have c times b minus a. C, that's the velocity, constant velocity. B minus a, oh dear, b minus a, that's the length of time, right? Because if we're going from a to b, then the length of time between those is their difference. So this number here, c times b minus a, that's the distance traveled over the time interval ab if the velocity is constant. That's sort of our first result. And now we're going to build on this to get something much bigger. Because obviously, we can't assume that the velocity of the particle is going to be constant. Any object that's undergoing acceleration has its velocity constantly change. So, in other words, every object ever, except for maybe a particle floating in deep space. However, there's a way that we can sort of get around this, philosophically. Let's suppose that the time interval over which we are observing the particle is extremely short. So short, in fact, that the best measuring instruments in the world can't detect a change in velocity over that time. Well, it's reasonable to assume then that over this extremely short time window, the velocity is in fact constant. I mean, if you can't measure a change, then it's got to be constant. Whether it is or is not in reality doesn't really matter. We have no choice but to say that it's constant. Thus, we're going to formally make the following assumption. If the time interval is extremely short, then the function f must be constant on it. Doesn't matter what function this is. And really, all that we're doing here is assuming that the function is continuous. This is identical to saying that the function is continuous. Saying that it's essentially constant on a very short interval. And every function we're likely to encounter in this course is continuous, so this is a fair assumption. And just to put this in other words, if a to b is a sufficiently small interval, and t star is any point inside this interval, then if t is any time inside this interval, the value of the function at t must be the same as the value of the function at t star, right? Because f is constant. If f is constant over this interval, then it's not going to change. You have two arbitrary points inside the interval, they have to agree because it's constant. Okay, so to put this in other words, we have the following big boxed assumption. And I'm putting this in a big box because this assumption is going to play a key role in a lot of what we do in the coming weeks. Really, in deriving a lot of calculus formulas, this assumption plays a key role, at least in understanding it intuitively. So if AB is an extremely short time interval, and T star is any arbitrary number inside that interval, then the distance traveled by the particle over the time period A to B is f at T star times B minus A, right? That's literally just this formula again. So the velocity is whatever we measured inside that interval, f of T star, and then B minus A is the length of time. Okay, now, suppose that the velocity is not constant, which we have to at some point, and suppose that the time interval is not witheringly short, which again, we have to if we're going to do anything practical. We're going to use the assumption above that the function is constant on small intervals to construct an approximation to the total distance traveled by the particle, right? Because that's ultimately what we're interested in, is we want to know the distance traveled. Now, we know that the velocity is constant on small intervals. So, let's take the whole interval AB and chop it into tiny subintervals. Subintervals so small that the function is effectively constant on them. In particular, we're going to sample n points. So x sub 0, which is equal to the left endpoint, x1, x2, x3, all the way up to xn, which equals the right endpoint. And then that gives us a bunch of subintervals. So x0 to x1, x1 to x2, x2 to x3, and so on. And we are going to we're going to chop the interval in such a way that all of these subintervals are extremely small, small enough that the function is effectively constant on them. Now, in addition to this, well, what else do we need? Well, we need some arbitrary point to lie inside the intervals. So let's do that. Let's choose n arbitrary numbers, xi star, to lie inside these subintervals. And then according to our assumption, the distance traveled by the particle over the time period of a subinterval is this guy. So the velocity we measured inside that subinterval times the length of the subinterval. Well, altogether then, the total distance traveled by the particle over the time period AB is approximately what you would get if you add up the distances of every subinterval, which is exactly what we do here. We're just adding up all of these little bits for every value of I. Right, so this index I here, this index I ranges from 1, 2, 3, all the way up to n. So just keep that in mind. Anytime you see the number I here, just recognize that that's an index. It's something between 1 and n. Those are our sample points. And then we can take this big sum and write it a lot more compactly if we use the summation notation right here. So recall, all this symbol means is that we are taking the sum of all of these dudes, as the index I ranges from the value of 1 to the value of n. So this expression here and this expression here are identical. It's just a much more compact way of writing it. Okay, so we have an approximation of the total distance traveled by the particle, but let's clean this up a little bit. Now we may as well choose to chop the interval into n pieces of equal length, right? Let's choose these subintervals to all be of equal length. May as well make things easier for us. Since the interval AB has length b minus a, it follows that the subintervals have length xi minus 1. Well, if we're taking AB and chopping it into n equal pieces, then the length of each subinterval is just b minus a divided by n, right? And that's going to be the case for every single subinterval. So because the length of the subintervals is a constant now, let us denote that length by the symbol delta x. So delta x is defined to be b minus a over n. So by the way, if you ever see me using this symbol, colon equals, that means by definition. So that means I am defining the symbol delta x to mean b minus a over n. In which case, the formula becomes slightly easier to look at, right? Instead of this, all of these lengths here have been replaced with the single length delta x. Now, finally, let's just note that the number of subintervals that we cut the interval into is completely arbitrary. We're assuming that the velocity is constant on each subinterval, but, of course, this may actually never be true. I mean, generic functions have an infinite amount of precision. So this is only ever going to be an approximation. But regardless, if the function is continuous, then the smaller we choose the subintervals to be, the closer to constant the velocity will be on them. Consequently, if we want to increase the accuracy of this distance measurement, we want to have as many subintervals as possible, because that way they're all going to be very tiny. So the accuracy of our distance measurement increases as the number of subintervals n increases. It stands to reason, then, that to obtain the true distance, rather than the approximate distance, we take the limit of this quantity as the number of subintervals n tends toward infinity. So the total distance is the limit as n goes to infinity of our approximate distance measurement. So this is kind of an intimidating formula at first, but you know, piece by piece, I think it makes sense. You know, chop the interval into subintervals. This is their length. This is the measurement on each subinterval. Add them all up, and then, you know, let that approximation get better and better and better and better towards infinity. Each piece in this formula has a very, very specific meaning, which I think I've, you know, described to it in as much detail as I possibly can. All right. So, although it is inspired by notions of velocity and distance, of course, it can be inspired by other things as well. For instance, you've probably seen the idea of taking the area under a curve and doing this exact same sort of analysis to it. I like to think of it in terms of velocity and distance, though. But the procedure described above can be applied to any function on any interval. Doesn't have to be velocity, right? Just follow the same steps and you'll get the same sort of quantity. So the quantity thus derived, in other words, this thing, is called a definite integral. And like I just said, in addition to distance traveled by the particle, we'll see in the next couple weeks, in particular, how this very same process can be used to derive other quantities of physical interest. So, area of a strange planar region, a region that's bounded by the graphs of functions. Volumes of certain solids, solids which are easily described, so to speak. The length of a curve, the surface area of a solid. Those are applications that we're going to explore in this course. And then even more applications are explored in Calculus 3, specifically three-dimensional applications. The point being that this is a ubiquitous quantity that comes into play pretty much any time you want to approximate some sort of physical quantity that has continuous variability built into it. So for the sake of completion, I include the full definition here. I mean, it's basically everything that I already said, except I introduce special notation, which of course you've seen before because you all took Calculus 1. So the integral from a to b of the function. So this dude on the right is called the Riemann sum, by the way. And this notation is really something special. This notation for the integral is really something incredible, because this notation, in a sense, kind of summarizes the entire process that we've taken up to this point. I mean, I like to think of it this way. Whenever you see this symbol, what does this actually mean? It means take the interval a to b, chop it into infinitely thin slices. Don't worry about what that means. Just imagine that they're extremely thin. And let's say that those thin slices have length dx. Well, perform a multiplication f of x times dx on each slice, right? Because every time you take a slice, that's going to intersect with the interval at some value of x. So just take that value of x, throw it into the function, and do the multiplication. And then add up all of these values for all of the slices. So that's literally what this is telling us to do. It means slice the interval AB into tiny slices of length dx. Perform the multiplication on each slice, and then add them all up. Which is literally what's happening, just under a limit process. In fact, you can even see how the delta x inside this formula under the limit process transforms into the dx symbol. Similarly, the sigma, which indicates a finite sum, under the limit process is transformed into an integral, which is, in this sense, an infinite sum, a sum over infinitely many tiny slices. Yeah, you can even think like the sigma, well, that kind of looks like an S. The integral, well, that kind of looks like an S. Over here, we've got all of these harsh angles. That sort of brings to mind finiteness, because this is a discrete sum of finitely many things. Over here, all of these sharp angles transform into this smooth curve of the dx, because now it's under a limit process, so it's a continuous operation. Again, all these sharp angles transform into continuous shape. It's really rather beautiful and poetic, the way that this notation encapsulates the ideas on display here. Indeed, this symbol is literally supposed to look like an elongated S to mean sum. Yeah. Okay. So our assumption, so this is all dependent, of course, if the function f is approximately constant on sufficiently small subintervals of a, b. And like I said before, that means that's the same as saying that the function f is continuous. And as it happens, if you assume that the function f is continuous, then the definite integral always exists, right? Because anytime you take a limit, there's always a question about whether that limit actually exists or not. So if the function we're integrating is continuous on this interval, then yes, the integral will always exist. Okay, so let's do an example. Let's actually compute this. Evaluate the Riemann sum for f of x equals x cubed minus 6x, taking the sample points to be the right endpoints. Okay, so we're going to chop the interval 0 to 3 up into a bunch of tiny little pieces, and then the sample points, namely the xi stars, those are going to be the right endpoints of the subintervals. And let's chop this into 6 subintervals. Okay. So chop the interval a, b, oops, I'm sorry, 0, 3, right? Because a is 0 and b is 3, into 6 subintervals. Namely, well, let's see. Let's see. I mean, we need to know what the length of those subintervals is going to be. So let's compute delta x. So delta x is b minus a over n. So that's going to be 3 minus 0 over 6. So that's going to be 1/2. Yeah? So our subintervals are, well, let's see, we're going from 0, and then we're going to go out 1/2, so 0.5. The next subinterval is going to be 0.5 to 1, right? Because we're just taking a distance of 1/2 each step. Then 1 to 1.5, then 1.5 to 2, then 2 to 2.5, then 2.5 to 3, and then we're done, right? Because we're just going from 0 to 3, and indeed, those are our 6 subintervals. So far, everything is working out. So our sample points are the right endpoints. So 0.5, 1, 1.5, 2, 2.5, and 3. So these are going to be the xi star inside this formula. Okay, so evaluate the Riemann sum. So we are just going to take, so we're just going to compute this quantity for each of the sample points and then just add them all up, right? That's literally all that we have to do. So it's f at 0.5 times delta x, and delta x is 1/2. And then I'm just going to copy paste. So the next sample point is 1. The next sample point is 1.5. The next sample point is 2. The next sample point is 2.5. The next sample point is 3. Okay? So there's the Riemann sum. What is the function in this case? Well, the function is x cubed minus 6x. So I will spare you the details of, I'm not going to actually write out the full thing. So like f of 1.5 is 1.5 cubed minus 6 times 1.5. I am going to assume that you can do that much. But let's see. So we have a 0.5 on all of these things here, so let's just factor that out. So we have 0.5 times, and then, 1 second, I'm sorry, let me get my calculator. Sorry, that's horribly unprofessional. In fact, for next time, I think I'm just going to do these computations beforehand. I mean, the whole lecture is being done beforehand, so why not do this as well? But so just sort of to make sure that you can do these same computations at home and, make sure that you get the same numbers that I do. So for the first one, it's negative 2.88. For the second one, I got negative 5. And I'm just truncating these to 2 places of precision here. Of course, if you keep the entire number stored in your calculator, then of course you're going to get much better precision. If you just truncate down to 2 places of precision at each step, then your final answer is going to have some round-off error in it. But for this particular example, I don't really care. So that's f at 2. F at 2.5 is 0.63. And then f at 3 is 9. Okay. So all together, so I'm going to do this next step entirely within my calculator so that I get as much precision as possible. Okay, so note to self. For exercises that have a lot of computation in them, just do it beforehand. I am telling myself. There we go. Yeah, so completely straightforward. Really, just make sure that you're able to get these same numbers at home. Okay. Now, estimate the integral from 0 to 3, x cubed minus 6x. So basically what we're doing here is we're doing this same process, but now, well, we're taking the limit as n goes to infinity, right? So let's just do the same process, but with n instead of 6 equal to, say, 100 or 1,000. And naturally, this is the sort of thing that we're not going to write out by hand because that's absurd. So we're going to write a computer program to do it. So the following code will work in GeoGebra. So I encourage you to just go ahead and plug this into GeoGebra yourself to see that it in fact works. So sum. So we're just going to do sum. Well, let's see. So the problem here is that we need to have some sort of formula that gives us our sample points. Because if we're going to write a program for it, then we need a formula to give us our sample points for when n is arbitrarily large. So let's see. So the sample points are going to be given by, well, let's see. We start at 0.5. So what was that? Well, that was a plus delta x. That was a plus delta x, right? That was our first sample point. Just, 0 plus 0.5. Our next sample point was 1. So that was what we got after adding yet another delta x to this. The next sample point we got after adding yet another delta x, and then another, and another, and another. So our sample points are given by a plus some number of delta x's. Well, how many delta x's? I of them, right? So the first sample point is a plus 1 delta x. The second sample point is a plus 2 delta x's, and so on, all the way. And we can, well, yeah. So in GeoGebra, we write sum, and then we write down the expression that we're going to be summing up. So let's see, a is 0, so it's just 0 plus I times delta x. Well, what was delta x? That was b minus a over n. Well, let's see, b was 3, so just 3 over n in this case. So we're adding that up. F at the sample point times delta x, so we still have to multiply by yet another delta x. Okay, like so. Then, comma. Comma. So this is the expression that we are summing up. And then next we have to put in the actual index that we're summing over. So that's I. So that indicates to GeoGebra that in this expression here, I is the index. And then I is going to run from 1 to n. So for n, you can put, well, anything. Right? And then that ends it. So this code will compute it for you. Incidentally, when you're in GeoGebra, you have to specify f first. You can do that easily. In GeoGebra, literally all you do is just type, f of x equals x cubed minus 6x, and it'll understand that. Yeah. And then in the next line, you would type, say, n equals 1,000. Or don't make it too big because that'll make it chug, or that could make it crash. Because if you're doing GeoGebra through the web application, then it slows down a lot when you try to put in big computations. But but this should work. In fact, I haven't checked it lately, but they may even have functionality to like put in like this big symbol here, so it'll look even more like the regular formula. In any case, you do this, you should end up getting something like, and now, one moment, I have to actually look it up. This one I did do beforehand. I'm sorry, this is a learning process for me. I'll try to make sure that there's less dead air moving forward. I suppose I could edit this, but I don't really have any editing software, and that's a lot of work. Anyway, yeah, you take n to be big enough, and you'll end up getting something close to this. Anyway, the point that I'm trying to make is that you should familiarize yourself with GeoGebra. Anytime you're doing like big computations, you can almost always do that with GeoGebra with like relatively little difficulty. So this is sort of an example of that. We'll do more of that in the next section when we're talking about numerical integration and looking over some other techniques for numerical integration. This is sort of the simplest technique for numerical integration that you could possibly use, which is that you're literally just typing in the definition. You can get a little bit more creative than that and get more accurate results with smaller n's. But as it is, in order to get this to be accurate, you want your n to be as big as possible. Okay, so for reference, here are a bunch of properties. I'm sure that you've seen all of these at some point. I'm not going to go over them in voice, just understand that they're all here, and I may refer back to these at some point. So just as a quick example, using a couple of these properties, well, let's take a look at this guy. We know that the integral from 0 to 10 is 17, integral from 0 to 8 is 12. What is the integral from 8 to 10? Well, that's going to use, which one is it? That's going to use property, no, not property 4. That's going to use property 7 right up here. So integral from a to c plus integral c to b is equal to integral a to b, right? So this c kind of cancels out. So with that in mind, we know that the integral from 0 to 10 is equal to the integral from 0 to 10. Well, that's equal to the integral from 0 to 8 plus the integral from 8 to 10. Right? We can break apart integrals in this fashion. Oops. Right? I mean, we know that for certain. So, just rearranging things, we want to know what the integral from 8 to 10 is. So that's just the integral from 0 to 10 minus the integral from 0 to 8. Oops. And that's precisely the data that was given to us. So 0 to 10 is 17, 0 to 8 is 12, so our final answer is 5. Yep, that's all there is to it. So just to bring to mind this property that you can break up definite integrals in this fashion along the domain, which, you know, if you haven't seen that in a bit, then maybe don't remember. Next, evaluate the integral from -2 to 2 of x to the 6th plus 1. So the trick here, and this is a useful trick to remember, this is going to use property 11. So if f is an even function, so what does an even function mean? That means that if I plug in a negative x into the function, that's the same as just if the negative was never there at all. The function eats negative signs. So if f is even, then the integral over a symmetric interval, so from -a to a, is just 2 times the integral from 0 to a. And you know, I'm just now realizing we don't have, so, okay. Sorry, I think I put this in the wrong spot, because we don't have the machinery yet to evaluate it anyway. Oh well. I'll change it to say this. What can you say about this integral? Well, x to the 6 plus 1 is an, hang on. I'm sorry, I don't want the bold text. So x to the 6 plus 1 is an even function. So, like I said, that means that if you plug in negative x instead of positive x, it eats the negative sign. So let's see. Well, here we have -1, right? I can write this as -1 to the power 6 times x to the power 6 plus 1. Well, -1 to the power 6, -1 to any even power is just 1. So really, that bit there just disappears. So indeed, it eats the negative sign. Plug in a negative sign, and it's the same as if it wasn't there at all. So by property 11 in this enumeration, we conclude the following. So then if we knew how to integrate this, we would be golden. Which, of course, we will get to later in this review. What about this dude? Evaluate this dude. Well, what can we possibly do about this? Well, as context would indicate to us, we're going to have to use one of these tricks. And indeed, this guy uses property 12. So if f is odd, which means that it spits out negative signs, so even means it eats negative signs, odd means it spits out negative signs, well then the integral over a symmetric interval is 0. And these integrals do have to be over symmetric intervals, otherwise this doesn't work. So indeed, -2 to 2, that's symmetric, -1 to 1, that's symmetric. So is this an odd function? Well, yes it is. So the integrand is an odd function. Indeed, let's see what happens when we plug in -x. Well, you may not remember this, but tangent itself is an odd function, which means that it spits out negative signs. So there's that. So tangent is an odd function, so it spits out that negative sign. As for these down here, well, we have a -1 squared, which is 1, and a -1 to the 4th, which is 1. So the bottom remains unchanged. So the bottom bit alone is an even function, but altogether the whole thing is odd. So indeed, you can see that if we plug in a negative x, we get exactly the same function, just with a negative in front of it. So by property 12, we conclude that this dude is equal to 0. And how convenient for us that that is the case. So yeah, I wanted to do at least one example of these guys because every now and again this trick ends up being super useful, especially later on when we're going to be doing integrals with trigonometric functions. These tricks are going to become a bit more relevant. So it's good to have them in mind. Okay. So, as the first example I did shows, computing a definite integral using just the definition alone is computationally expensive. You need to take the number of subintervals to be extremely large. Now, given that the definite integral arises from consideration of positions and velocities, it seems reasonable to think that derivatives and all the rules used to derive them, or all the rules that we use to compute them, can be brought to some advantage. I mean, after all, they're coming from the same sort of thought experiment, of the particle moving in a straight line. So you would think that derivatives can be used to some advantage. And indeed, that's exactly the case. So let us suppose that f represents the velocity of a particle moving in a straight line over the time interval AB. So same setup as the thought experiment that we started with. Being a velocity, it follows that f of t is the derivative of some position function, right? I mean, that's what velocity is by definition. Hence, by the discussion above, the definite integral of f is the distance traveled over the interval AB, right? That was our main conclusion of the first chunk of the lecture. But now that we actually have a position function associated with it, what is the distance traveled over the interval AB? Well, that's literally the position at B minus the position at A, right? That's the distance it traveled. It's wherever it was at B minus wherever it was at A. It's the difference of the two positions. So this is what's called the second form of the fundamental theorem of calculus. Practically, it affords us a strategy for computing definite integrals. To integrate a function f, find a function big F, which satisfies big F prime is equal to little f, right? So in other words, find a function big F whose derivative is what we started with. So differentiate in reverse, and then just evaluate the right-hand side of this formula. Incidentally, we have a special notation for this dude. We just say that this is big F at x, and then we put a straight line with an A and a B at the top. So this means, that means, oh, I'm sorry, I put that the wrong way around. It should be like this. There we go. Yeah, so that means plug in B, plug in A, take their difference. Okay, so now we have the tools necessary to evaluate analytically, in other words, without expensive computations, this integral. So what do we want to do? Well, we need to find a function whose derivative is equal to x cubed. Well, by the power rule, it's not too hard to see that that function is going to be x to the fourth over 4, right? I mean, if you differentiate this, you bring down the 4, so 4 over 4 becomes 1, and you subtract 1 from the exponent so that you get x cubed. So, indeed, that's all there is to it. And then we just have to evaluate that between 1 and negative 2. So let me make a line break here so that it's easier to look at. Well, So let's see, that's 1/4. Incidentally, because 1/4 appears in both of these terms, I can just factor it out. Right? So we just have 1 to the 4th minus negative 2 to the 4th, and I just factored out that 1/4, since that's going to be in both of them. So let's see. So that is 1 minus negative 2 to the power 4 is positive 2 to the power 4, so that's 16. So 1 minus 16 is negative 15. So there we go. Okay, so I'm going to break here because we've gone over 50 minutes, and the typical lecture time is just 50 minutes. So I'm going to take a break, and then I will make another video, which will also be no longer than 50 minutes, which covers the rest of the review. In particular, we're going to do a whole bunch of examples. So just imagine that this lecture was our Monday lecture, which under normal circumstances, this is what I would have said on Monday. Okay, thank you very much.